Hey folks, welcome back to Domotro's room. Today we're not in the combo classroom, but not because it's raining. We got lucky on the rain today. We're not in the combo classroom because I am still upgrading it and am now in the process of that modular reset toward grade -2 I mentioned. And we will be tidying some things up back there and due to that process needing to stay somewhat secretive, you're not going to get to see all of it. We may get a sneak preview of some of the outdoors a little later tonight, which will be a stream I will be doing at my evening. I was going to probably do it at 6 p.m., but to make sure I can get a cool scene filmed first for an important episode, the evening stream will be starting a little later at my 7:30 p.m. Pacific time. And as for the square root of 64 here, and anyone else who may have been in that last attempt at a stream, my Wi-Fi was being really awful for some reason, and now it appears to be back. So usually it's alright, not the best ever, but once in a while it fully crashes and gets completely glitchy. So that happened at a bad timing, right when I had scheduled that stream. Now hopefully we'll be a little better, if not perfect. And as for people who did not see my last streams, yes, I currently have half of my hair approximately. This was because some people mentioned that I should cut all my hair, and some people mentioned that I shouldn't cut the hair, and so I averaged all the responses, and then I calculated that about 40 to 50% of people wanted me to cut my hair, so I cut 40 to 50% of it off, starting from this direction. Now, it'll make a little more sense in the context of the finale that I'm filming this for, and I will be shaving the rest of it afterward. So we'll be going into grade -2, looking a little more clean shaven and a little shorter hair, and then we'll let the cycle continue. Might not cut my hair during grade -2. We'll see how wild we let it get. But at the beginning we'll look a little fresher, and for the final episode I'm filming for grade -1, I will be looking a little off-center. We get half of the early grade Domotro and half of the late grade Domotro. Now, thank you to whoever asked how I'm doing. I'm doing well, and today I'm filming some exciting stuff. Today I will be filming a field trip scene, among other scenes, for a finale episode. Not going to say exactly what the field trip's about, because that finale episode's full of little surprises like that, and it'll be coming out in maybe a week and a half or so, toward the end of March, maybe in a week if I'm done by then with it, and probably closer to the end of March though. And that will be on the main combo class channel, where I did just put out an episode that I consider the final exam of grade -1. Completely optional, don't let me scare you away from the channel if you don't want the test, but it's a different test. It has a few sections, a mathematical problem-solving section, as well as a few other sort of appreciation and opinion-based sections. So make sure to check out that video or the text form of it that's in the description of that video on the main combo class channel if you want to, whether or not you want to consider taking the test, if you want to just see my views about tests and what sort of wacky test I would have put together. And although that's the final exam, it's not the final episode. It's sort of the culmination of most of the math. There's not going to be a crazy amount of math in the finale episode, and I'm going to be relatively busy this month working on that, so there's not going to be a crazy amount of shorts. There will still be plenty of mathematical live streams such as this one, which I will get to our mathematical themes in a moment. And in general this month, the main math arc has passed, but the coolest math topics I will be filming in early April and May and stuff for grade -2, because some of my favorite topics didn't fit in grade -1. We will be talking about some mathematical things in these streams though, because as we can see from today's title, although I'm late for Pi Day, I want to make a few remarks about pi. Pi Day is what some people call March 14th, due to that date sometimes being written 3 followed by a 16. by 14, which today would be 3 followed by a 16 in that format, and 3 followed by a 14, you could say resembles pi. 3.14 is the beginning of the decimal representation of pi. Now, that is a little biased, of course. We count in a base 10 system, and so we're gonna maybe base our holidays around that numerically, but it is only the base 10 representation of pi. Pi would, of course, look differently when expressed in a different base. In fact, if we expressed pi in binary, it would have more than one digit as the whole number part. Because to express 3 point something in binary, it would be 1 point something. So in binary, pi would begin with 1 before the point, not even a 3, let alone after the point. That would be completely different, which brings me to one of my thoughts about pi, which is that humans are spending a lot of time and computing power to try and find further digits and or patterns in the digits in pi, but only in the decimal representation mostly. I haven't heard as much news about them catching up the base representations being cataloged somewhere of how pi looks in other bases to make sure there's no patterns that we've missed in those. What if, for all we know, there wasn't any interesting pattern popping out in the first trillion digits of pi in base 10, but like 10 billion digits in some other base, there might be something notable. Maybe pi has some trait that relates to divisibility weirdly that mathematicians didn't predict. That there's no reason to suspect that, but could be true, and we always want to look for possibilities. And maybe pi wasn't dependent on the 2s and 5s that make up base 10. So in my opinion, we should shift a little of the computing power that is taken to calculate further digits of pi, and for one, catch up the other bases, how pi looks in the other bases. We also could catch up other representations of pi, such as its continued fraction. And that brings me to the point I'm going to have to shrink the screen where I won't see the chat for a minute, but I will pop back to the chat to talk to you guys in a moment. And here we can note, first let's just see for fun, what does it look like when we say pi in binary? So, yeah, 11.001, and then, we've proven it's an irrational number. So we know that in pi, in any base we write it, there will be at least 2 digits that alternate in a non-repeating pattern infinitely. And probably all of the digits in a given base alternating in a non-repeating pattern infinitely, but we haven't proved as much about pi as some people think. We have not proven, for example, that pi contains every single type of digit string. There is a unlikely but possible chance that pi stops having 8s at some point. There's a even less likely but still possible chance that at some point pi devolves into looking like just 0s and 1s, but we know they're not repeating. The pattern must be irrational. But we still don't know that thing that many people assume about all the digits of pi. Now, what I really brought this up for was to look at pi's continued fraction, which they're not really explaining it here, but I did make an episode about this, so maybe we can get them to show it a little more here. Pi continued fraction. Now, there are many possible what is called a continued fraction for pi, one of which is called the general. Well, there's a generalized one, but this is the simple continued fraction. So we'll look at this first. It's up here. In a simple continued fraction, all of the numerators in this weird infinite chain are 1. And what we have here is this infinite fraction, 3 plus 1 over 7 plus 1 over 15 plus 1 over... And we'll notice that it's a weird pattern here. It does not look like this repeats from you looking at it here, and it's true that pi's continued fraction is not periodic, although some other ones are. If I look up square root of 2 continued fraction, it actually is periodic. The denominators are all 2's at this point. And even square root of 3, it's going to have a slightly longer period. It alternates 1's and 2's in the denominator. But some things, for example, the square root of a non-square integer, have really messy decimal representations, but actually have a period in the continued fraction representation. Now, there is an episode about that on the main combo class channel. Make sure to check out the continued fractions episode if you haven't. But what I just wanted to note here is that why don't we put as much study into what the next denominators are here as we put into what the next digits are in base 10? I would argue even more important than calculating pi's digits in any base is this base-independent trait. No matter what base I write this in, it'll be how that base writes 292 there. These will be 1's, and it's the same thing translated. Unlike a decimal where every single part of it changes in a non-referential way, where it's all different. Here, it's base independent. We could translate each little part of this into a new base, and it would still be true. So I could even write these with an amount of dots and avoid it being a base at all, just making dots. Now, why don't we study the next denominators in this as much as we study the next decimals? So, there are many denominators of this studied, but not nearly as much as how many decimal digits we've calculated. Now, there are general continued fractions as well that look quite interesting. And do they not have these as the fractions? Well, you can check out my episode about those if you haven't seen, but there are ones where if the top is not required to be a 1, there is a pattern that some of them are like, these all go up, all the even numbers, and these all go up another thing related to the numbers. And some of them have a very clear pattern, yet equal pi, in the sense that, yes, it's infinite, but we treat it as what this infinite thing approaches, and so it is approaching the limit of equaling pi. So, let's spend more time studying stuff like that. Now, let me quickly explain, while we have this calculator open, why I did call today square root of 10 day. Well, if we call 314 pi day, the square root of 10 is 3.16, and then a small enough number that whether we're rounding or just including digits, we got 3.16 if we truncate it there. So there we got square root of 10 day by the same logic that 2 days ago was pi day. So square root of 10, the closest square root to pi, although if you're going for roots that are close to pi, cube root of 31 is shockingly close. Very strange coincidence. Cube root of 31, 3.14138. Pi starts 3.1415. Speaking of the decimals in pi, funny enough, I was on pi day, although I didn't make content here. I did eat a pie that had a pie on it. So I ate a pie at my friend's place. So did celebrate Pi Day and did watch this movie. We watched the movie Pi, called Pi. And although it is a good movie, I must note sorry that this will be a roast to the movie. It was interesting. It was experimental. It was cool. It was about a mathematician. So I'm not a big movie watcher, but the experimental ones I'm more likely to like. That was pretty interesting. However, there is one problem. They wrote pi in the opening credits, and they got barely any of it right. They got the first 8 or 9 digits right. After that, it was just random characters. They do that in a lot of movies. If they say pi equals something, don't trust them. They sometimes think that after the 3.14, the viewer just stops caring or checking. But I checked, and they only got 8 or 9 digits in the opening credits of that movie called Pi. So, good film, bad double checking on your numbers. But In any case, I do remember off the top of my head that pi does start 3.141592653 at least. And then I want to say 58. I'm not positive. Because back in the day, me and my friends memorized like 100 digits of pi as a challenge of who could do it first in like middle school. Or for people in other countries, that's when you're like 12 or 13. And so some of it just stuck. I don't think I'll ever be able to get the 3.1415926, at least that part, out of my head. So, in fact, that's enough to calculate a lot of stuff. To need more digits than that, you would have to be at like a microscopic scale compared to like a universal scale. It's debatable, in the universe, we actually don't know to what degree a perfect circle has room to exist. If you zoom in and things are forced into more of a grid-like pattern or anything, we don't know really. But I personally believe that whether or not you say circles exist in nature, I think you could say they exist as a limit that is approached in nature. There are rules for mathematically what makes something circular. And we could say that things are circular in nature if they are approaching that. Whether or not they are perfectly there, as a limit, I think we could say things are circular. So, similarly, here in Mathland, where we can create landscapes that can purely follow the numbers, we can graph a lot of things that get pi in them. In fact, funny enough, when I graph the thing that encodes pi, basically, or the first place you'd look for it, a circle, and that's not the only place that pi is encoded, of course, because pi will show up in the equation for spheres, for hyperspheres, and so on. And arguably, the fact that pi is the ratio of the diameter to the circumference, or the fact that it is pi r squared gets you the area, neither of those on their own are that interesting. There had to be a number that was the ratio. I can see this is a length, I can see that's a length. There's some ratio between those lengths, whether it's a ratio of 1 or 2 or 4. In this case, an irrational number, which is one thing interesting, is that it is an irrational and transcendental even ratio. But the first interesting thing you'd encounter as a historical mathematician, probably, this is just my personal guess or philosophy, isn't, oh, it's so interesting, the ratio is 3.14. You can gauge with your eye the ratio is somewhere a little bigger than 3 if you tried to measure it, and there is a ratio. What would be same with the area. If I said, oh, whoa, this squared times this thing called pi got me the area. Well, of course, there's going to be some number I could make that equation work for. But what's interesting is that it's the same number in the area formula and the circumference formula. Not just that the circumference is pi times the diameter, or that area is pi times the radius squared, but that it's the same number in each of those. That as you go up a dimension and change something, looking at a different dimension of size, and you could play the same game and note pi does still show up in volume of spheres and onward, that on the different dimensions, pi is in each of them. So that to me is one of the first most interesting things about pi. It is over anything circular, almost regardless of dimension. So, funny enough, with my circle equation here, it would be hard to see the number pi on the graph anywhere. I know that it's the ratio of that outside to the way across, but I can't really see the number pi as a coordinate or anything on this graph. However, we've seen pi as a coordinate point, or multiples of pi, or powers of pi, or stuff like that, in all sorts of equations we've played around with in the past. And that's because we've messed around with trig functions, and a lot of those are periodic on cycles that relate to pi. We've messed around with things that are throwing things like sine of something, or cosine of something, or tangent of something into graphs. Now, these are trig functions or trigonometric functions, and they happen to have a lot of pi related stuff going on in their period lengths. We can see pi right there. Both of them hit it right there, pi. They even label it as pi. We can see other spots. Ooh, look, there we get 666. No, it's just where they truncated 2/3. And pi fourths, those ones hit at. Then you get, the next time those hit is at, where are we? 9 pi over 4. Now, let's make these inequalities to start, where we're going to say y is less than sine of x, y is less than cosine of x, and y is less than tangent of x, just because that's what I had in the thumbnail to make a fun little landscape, even though it might be different colors this time. But this, although we see pi in some crossing points, and we see it's like where they bump on the axis again, so their full cycle is 2 pi to get back where they fully are repeating themselves. There's another way we can see pi show up all over. One that we've noted is if you multiply, and we're going to put these on the same side this time, sine of x times sine of y, where the sine of the x coordinate times the sine of the y coordinate equals something, and we'll say it equals 0, gives us this grid. Now it's centered in a way where we can see that it's like oriented a way we might expect or like, but it's not a multiple of 1, it's a multiple of the length of the square of pi. These squares are pi over pi up, and therefore the area in it is pi squared because it's a square of pi. So we could also make this an inequality and say when are they less than 0, and you get your checkerboard. So what if I wanted to have them not be pi in there, and I wanted to find a way to make them the grittiest grid ever? Straight oriented, alternating black and white like this, but its size of square was 1 by 1 squares. Well, let's put a coefficient in these before the x and the y and see how, if I have sine of something times those is less than 0, we can change the size of these fellas. So where are they 1? Well, when we go to where they're about 1 on my slider, we're at 3.1. And it's true that, let's see, can you even see the slider? You might not be able to see the slider. Let's get rid of this. So here we have 3.1 is where that makes it about 1, and pi is where it makes it exactly 1. So funny enough, when I don't have pi in there, when I have 1 in there, the squares are pi-sized. And when I have pi in there, it shrinks down to being 1-sized. So it turns out if you want the grittiest, checkerboardiest grid you'll find as a graph, it's where sine of pi of x times sine of pi of y is, you could either say less than or equal to 0 to get that, or very similar if we say greater than or equal to 0, it just switches which ones are black and white. So that is a pretty almost like practical grid to think about. If we say when is it equal also, it's a grid. I'm getting a grid right here. So that's kind of fun. And let's put these fellas back on there. And in fact, we're going to take the pi out, because now we'll see that if I make my grid with the, and we'll change this color so it's a little lighter. If I make this grid without the pi in there, now it has pi as the increment. When we're not seeing the pi in the equation, we see it on the graph. And so they are now hitting at the similar points. Bing, bing, bing. Now, the one I showed in the thumbnail was a little cooler even, because I added one more variation. And it's kind of the simplest variation you could think of, which is, well, I'm multiplying them right here. What if I added them instead? And really, when I find all these interesting patterns and shapes, that's half of what's going on in my brain, is just, oh, I haven't tried putting a plus there. There's times there. Let's try putting a plus there instead. It's a lot of just fiddling around and having fun. And you get interesting little landscapes. This one is a pretty methodical, repetitive landscape. If I zoom to the side, you know, it looks the same as if I zoom over here, but still pretty neat. Now, if I want to make these a little wackier, what I could do is taking just the grids right now, let's square them to start. We're going to square the y and the x. No. And what's happening is when we have a squared in there, things are going to be changing at different rates because, like, it takes longer to get it from squares to one number from 0 to 1 when we're trying to get to the square, or from up to 2. Or backwards, depending how you look at that. Now, here, when we square them, they stretch out a little more, and they go outward a bit. Now, we can even, if we just have one of these, get a sort of illusion. Well, actually, we get a little bit of it here, where it sort of looks tilted or curved on the sides of these, but I can get that more so. You guys want an optical illusion? Well, here's what we're going to do. What's, in a weird way, the opposite of x squared? Well, you could say square root of x. That is, in some weird ways, the opposite of it in some ways, because what that would be doing is taking, instead of x squared, x to the power of 1/2 for looking at our principal square root. But another way we could think of it is x squared is xx, x times another x. To go backwards from x would be dividing by x. So in a weird way, the opposite is backtracking to like 1. In a weird way, what I mean is we need to double backtrack. What I want to get to is 1 over x. But we can write that as x to the power of -1. So, you know, x to the power of -1 is our reciprocal here, but I'll write it as 1 over x in case that gives the computer an easier time. Well, when I say sine of 1 over x plus sine of 1 over y is less than or equal to 0, and we're going to do it with multiplication as well. Zoomed out, it does not look like too much wild stuff. Looks pretty boring from this scale, but if you zoom in, let's remove this one for now and look at this. This one is the optical illusion-y one I meant. Don't these look like curved pillars sort of plummeting downward or upward? And that center zone is where it gets infinitely dense and gives the computer a hard time trying to handle it at different levels. So that one's neat looking. This one also is pretty cool, but in a more square way. This one, the reason why I mentioned this has some traits of being the opposite of x squared also is we noted that that one went outward, getting smaller, the x squared version, and then gave the computer a hard time. In fact, let's put it this way. X to the power of a. Y to the power of a. And we're going to give ourselves a slider for that. Now, with 1, don't have much. With 2, we're going to do it with this one as well. Let's see. There we go. We are in the middle of the blank spot. I was like, what's going on? Why aren't I seeing the graphs? We are inside them. So here, if we have one at a time, to the power of a, the state of 2, we see we get a squarish big center here, and then they get smaller, 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 getting infinitely small. Whereas -1 kind of felt like the opposite in a way, because we have these big squares out here, and then we go in and we get infinitely dense near the middle. We could also go to the power of -2, which is like 1 over x squared. And get that. And for some values in between, when it tries to get them, we only see 1 sector. And if we do the 0th power, we're not going to get anything cool, because this will turn those to 1. So, what about the other one? Somewhat similar games. Here we're up at 2. Here we go down to like -1s, and the infinite density is sort of on different sides. So now, just since it is square root of 10 day, let's make the square root of 10 show up somewhere in a graph. So what are some traits square root of 10 has? This is a new game I realized we could play. Is you come up with some traits something has, and then you write in equations where it would fit that at a certain point. For example, what are some equations where 1 plugged into it would give you square root of 10? And then we'll see those ones cross right there. And yeah, we can do it. Well, let's make 10 hit square root of 10. So first we'll say y equals square root of x, and for sure 10 is there. But then we have to go upward at 10 there to meet it. Can we make another one that hits there? Well, square roots are tricky numbers. What we have right there, I guess, is square root of 2 times square root of 5 happening there. So what are some other ways we could pass through this point? Well, in any case, if we needed to go really simple, we will make our merger for now be x equals 10. And we know for sure those meet at the square root of 10. Now, the square root of 10, as well as pi, and their closeness, does have importance in one of the fiction books I've been writing. And one of the fiction books I will publish at some point. You'll have to be on the lookout for square root of 10 and pi and their similarities or their proximity on the number line being relevant. So, sorry that I wasn't really looking at the comments throughout this stream. Let's make our background a little more colorful by trying one of these cool ones. Well, let's just do one of these classics on the wall for now. And then I'm going to take a little peek at the comments. We're not going to be streaming super long for the morning stream today, because I actually am going to be streaming tonight too. It's going to be an extra rare stream. And I mean my tonight, where it's going to be in like 7 hours from now or so. I'll schedule it. It's my 7:30. I will be streaming again, partially because I mentioned weekly Thursday streams where I'll mention some stuff about a weekly puzzle. So I will be going over some puzzle-based stuff then. But most of the evening stream will be special and rare because I'm not going to spoil it all today, but after I do a cool field trip that I'm filming today, there's a good chance that we'll be at the right state of setup of the transition in the classroom to film something cool outdoors there for our stream. So we'll probably have an interesting outdoor nighttime stream, and that will be coming in a little over 7 hours from now or so. And I will also schedule that in a little bit, so you'll be able to see it at least a few hours before it happens. And today I'll be filming some very rare stuff for the finale. So thank you all for the comments. We also got some comments about pi versus tau. Now, I'm okay with pi. I know a lot of people think that the constant representing 2 times pi would simplify some equations, but there are also other equations it wouldn't simplify. It would be somewhat of a fair trade. Now, there's logic to the argument that we should switch pi, but I'm not very strongly on that side. So, while I can see the logic, I am personally okay with the number pi. However, we'll give a shout out to its friend tau, which is the Greek letter used for twice it, which has many applications to geometry. So let's see. Someone also mentioned July 22nd, which is 7/22, because 7/22, which some dates look like that, like this divided by that. 7/22 is a good approximation for pi. So that's a good one as well for pi approximation day. That will be our day for sloppily created circles. Circles that are a little off from pi because they were man-made by someone with less expertise. So like when I draw a circle in one of my videos, that is probably closer to having something like 22/7 be its thing. And wait, yeah, if I said 7/22, I mean 22/7, of course. You need the 22 on the numerator for that to be close to pi. So thank you for all of the comments here. And a lot of these are visualizations that we could view as triangles, like someone mentioned, because these trigonometry things are related to pi, but really they are defined in terms of triangular stuff pretty much. And yep, thank you all for joining me. And someone's wondering, is there a name to the volume of a sphere? I'm not sure what you mean, because like kind of like area typically is assumed to mean 2D. Volume is typically assumed to mean a 3D thing. So you'd say the volume of a sphere, like you'd say the area of a circle. Volume's a little more confusing because sometimes when you go into 4D and 5D stuff, you use volume to refer to the hypervolume going on at different levels. Because, you know, if I say hypervolume, then do I mean just 4D or do I mean 4D and upward? It's a little ambiguously used. Some people, you know, use it in different ways. So you want to be clear before you start talking about your 4D geometry. If you use the term volume, if I mean, no, I do mean like the amount of volume it has at that scale and not the hypervolume inside it. But for example, a 4D version of a cube could be said to have a hypervolume enclosed by surfaces with volumes. And so, which are then enclosed by surfaces with areas, which are enclosed by surfaces with perimeter distances, which are enclosed by dots, which are points and are the 0th dimension. So it's a little ambiguous when you use volume, but typically, unless specified, volume would mean just the 3D case. And if they meant similar to perimeter, then perimeter doesn't really get a special name because perimeter doesn't just mean for a circle. You know, you could talk about the perimeter of any shape. You could talk about the surface area on the next one. So surface area might be the word you're looking for if you're looking for something similar to perimeter, and volume is similar to area. But all of them, you need to clarify that you're talking about a circle. In fact, the circle isn't the one that got too many nicknames. Square-related stuff got too many nicknames. We call stuff squares, cubes, rectangles, quadrilaterals. There's so many more terms for those. And squares really are like the regular fourgon. Sort of like we would say a regular hexagon to mean the 6-sided one. And instead of a regular tetragon or something like that, or regular quadrigon, we went with square because they're a little more common in some aspects of reality, but they got a lot of credit. So squares need to share some of the credit with circles and triangles, two shapes that are at least as fundamental as squares. And, you know, there's so many ways we could define squares and rectangles and stuff with different combos of the nicknames that are used to refer to all sorts of different quadrilaterals. Even quadrilateral gets like this whole different name. You're like, if you're going downward, think of them. You're like, okay, I got a hexagon, a pentagon, a quadrilateral. I got a triangle. And then you get, so triangle's a little different too. Then you get for the regular one, regular hexagon, regular pentagon, square, equilateral triangle. Oh, come on. We got to fix up the terms for the threes and the fours to be a little more similar to, if you're going to set a trend where like all the rest of the shapes are, we call it regular word root gone. Can't we just stick with that for the first two polygons as well? This triangle and the square. I honestly think they should be rebranded. And maybe, even though it's an extra word or two, once in a while, just to spite all of the square obsessed people, I will have to call squares regular quadrilaterals. So, and oh, you're right. The perimeter isn't a term for that, but circumference is a special name. So you are right that, of course, we do have one for that, similar to how circles do get a name for their diameter and their radius. So you are right. We do get a special one for that. Although area, we do have to still mention we're talking about the area of a circle, interestingly. And so I guess on the first level there, circle did get an extra nickname just on the description of that 2D length. I mean, well, a 1D length that's looped through 2D space, but 1D. So we aren't going to stream for too much longer because my main camera fellow Carlo will be coming by in like 30-40 minutes or so. And we are going to film a little more finale stuff here before taking a little field trip. Then filming some more rare stuff here before later in the evening I will be doing that evening stream outdoors. And that will be quite rare. That will be maybe a little less mathematical, although we will include puzzles, but you'll get some very rare clues of what's going on in our transition to the next grade, and it will include some fun activities. So, hope to see some of you there, although usually it'll be a different set of people due to time zones and all who join the earlier or later streams. It'll also be available as a video to watch later. Make sure that you've all checked out the final exam video on the Combo Class channel too. Not on this channel, but on the Combo Class channel, the last episode that's fun to watch whether or not you want to try my weird version of a test. But I do recommend also, after you watch it, considering giving a shot to parts of it. And I think we are going to wrap up our Square-Root-of-10 stream about there. So, as usual, thank you all so much for joining me. If you want to follow further, there is, the Discord where I chat with people when I have time, as well as the Patreon if you want to be super extra helpful and get some bonus stuff, and also a subreddit and things like that. So cool links in the description. I will add some timestamps at some point today to this stream, not sure how soon, for people who missed earlier parts of it, but we were mostly just chatting about some pi related things, although yes, it wasn't on pi day, it was on square root of 10 day, I know. So here's another way we could define the square root of 10 geometrically. We could note that, let's see, the square root of 10 would be if I made this triangle, the triangle bounded by what I'm about to create. Anyway. Let's see. So here I have a right triangle with height 1, and this side is 3 across. And so by the Pythagorean theorem, the hypotenuse must be the square root of 1 plus 3 squared, because 1 squared is itself. So this sector of line between there and there, the diagonal of this, is square root of 10. So there's one geometric place it comes. We could also note that if I had a square with area of 10, its side lengths would be... If I had a regular quadrilateral with area of 10, it would have side length of square root of 10, which is about 3.16. And and thank you all for the nice comments and thoughts. I will be seeing some of you later tonight in that other evening stream. And for now, I have some interesting filming and field tripping and so on to do, most of which you will only see in the finale, but that will be a very cool episode. So, hope to see you all again at some point soon. Have a super good day, and I will see you later.